Hi and welcome to Geeks for Geeks. Today we would be discussing the video BST to greater sum tree. So before moving forward, let us first understand this term, that is BST. So BST is nothing but a simple binary search tree. So now what is binary search tree? Binary search tree is a tree where suppose this is the root, okay, this is the root, or suppose you can portray it as a head of the whole class monitor of the class, okay, and this is the left child, this is the right child, where the left child, the value of the left child would be less than the value of the root, and the value of the right child would be more than the value of the root. Okay, so suppose this is 5, so this should be 3 and this should be 6. And the same property where I can say that left is small than root and right is greater than root, this property should be maintained by all nodes. Okay, and if this property is maintained by all of the nodes in the particular tree, then it is known as binary search tree. Okay, so now let us understand the problem. So we are given a binary search tree and we need to transform it into greater sum tree. Now what is greater sum tree? Greater sum tree is a tree where each node contains the sum of all the nodes greater than that node. Okay, so let us see, suppose we come across 2. Okay, so what are the nodes that are greater than that? So 1 is not greater, 6 is greater, so we would add 6, then we have 3, not 3, then we have 7. So 6 plus 7 equals to 13 at the moment. Okay, then we come across 1. So if we come across 1, the values that are greater than that are 2. Okay, this is 2 is greater, 6 is greater, 3 is greater and 7 is greater. So basically every one of them is greater. Okay, so 7 plus 3, 10, 10 plus 8 is equals to 18. Okay, then we are told that 6, the only value greater than 6 is 7, so we would only have the 7th value. Then we have 3, the values that are greater than 3 are the 6 and 7, so 6 plus 7 equals to 13, and the value greater than 7, there is no value, so basically we would have 0. So now how this output is coming in? So this output is nothing but the in order traversal. Now let us understand what is in order traversal also. So in order traversal is the traversing from left. We would first visit the left and then we would visit the root and then we would visit the right itself. So now let us copy this tree and then we would do the in order traversal and then we would match our output. Now what we would do is we would build, so now what we would do is we would first go to the, suppose this is the root, so we would first go to the left child. Okay, so left child is having the value 18. Now left is visited, so if the left is visited then only we would be going to the root. Now we would be going to the root, that is 13. We have visited 13. Now after root is done, we would go to the right, that is 7. Now 7 would be the root, so roots left should be visited first. So we would again visit 13 and then the root itself and then 0. That is why the output to this is this itself. Okay, so now let us observe a very good thing. Okay, so now when we talk about the in order traversal, we would just take this true root itself and then I would do the same traversal once more with this one. So what we do basically is we first go to rec of, okay, first we would visit, suppose this is the root itself. Okay, this is the root, so we would first go to the left. So this root's left is nothing but rec of 1, in order 1. Okay, in order traversal, we are doing a in order traversal. So basically here we are doing a in order traversal with the inputs amount. So first we would visit 1. So now 1 is visited. Okay, then we would go to the root because now left is visited, left is done, so we would go to the root. Okay, so now root of 2 is visited, so we would visit 2. Then after 2 is done, then we would visit the left child. So we would visit the left child. Okay, that is this one. Now this one left should be visited first, then only we can visit this. So now we would visit this 6 would make us visit 3. So we would visit 3. Then the root itself, because we saw that left, then root, then right. We need to do this. So we would go to the root itself. After left is visited, we would go to root. So root of 6. So we would visit this. Then the left part of it, that is 7. So now we would visit this. So if you observe this, then you would find that this is printing the order in a sorted form. Okay, in a sorted form. So if we reverse this, we would have 6, 7, 3, 2 and 1. We would have this. So now we can say that we would have a prefix sum kind of thing. Okay, we would have a prefix sum kind of thing. Like for 7, we don't have any values that are greater than that. Why? Because we already know we don't need to traverse on that side. We don't need to traverse on the right hand side. Why? Because on the left hand side, we already know that we would have the values greater than that. Here we would have the values lower than that. Because in order traversal, in order produces in sorted form. Okay, this is a fact and you can observe it also. It is a very quick observation. So we know that the values that are greater than 7 that are in this BST would be lying on the left hand side, not on the right hand side, because it is sorted. So now we would go to 6. So we will simply say whatever value is there on the left hand side, we would have that. So for 7 the value would be 0. So for 6 that value would be 7. So for 3 that value would be 13. For 2 that value would be 13 plus 3. So that value would be 6 plus 9 is equals to 16. Okay, and then for this, that value would be 16 plus 2, that is 18 itself. Okay, we have this. So now if we have this, then we would see that 18, 16, 13, 7 and 0. 18, 16, 13, 7 and 0. And this is how the output is coming in. Okay, so if somehow we can already visit that in sorted form, okay, like if we come from the back, okay, this was sorted, we just reversed this and we found out that reverse is solving our purpose, that whatever is visited up till now, we would simply add that. Whatever is visited up till now, we would simply add that. Like we came here, 0 plus 7, we added it here, then 3, 7 plus 6, 13, then we added here, 13 plus 3, 16, then we came here, then 16 plus 2 here. So that's like a prefix sum kind of thing. Whatever value is there plus the current value. Whatever value is there plus the current value. If you don't know about prefix sum, consider pausing the video now and get the idea of it. This is how you would know how to relate the algorithms. Okay, how to relate the algorithms. So now we know that doing this left root and then going to the right part would produce in sorted form. Okay, that is from low to high, and if we do this reverse way, then that would be nothing but right root and then left, and this would have from high to low. Okay, sorted in the reverse order. So we would have this. So now what we can do is we can simply do a reverse in order traversal, and we would keep a sum that we have encountered up till now, and we would add that value whenever we have the current value, like I'm telling you. Okay, so let us implement this, and then you would get, then I would do the dry run and you would get a proper understanding of it. Okay, fair enough. Now let us move to the implementation part. Okay, so now we would start coding this. So now we would have a wrapper function. Why do we need a wrapper function? Because we know that here only root is there and the return type is void. So where would we keep the sum? This tells us the need of it. Okay, so we would keep this as void and we would name it as rec, because simply we are doing a recursion. And then what we would do is node star root, we would have the root itself, and then we would have the sum with pass by reference. Why? Because we want the sum to be changing, so we would pass by reference. Okay, so now if the root is equals to null, okay, if root equals to null, then we would simply return from that position. Okay, or if you don't want to write this long, you can simply write this if the root is not true. Okay, this would be condition that root is equals to null. Then what we need to do is we need to do the reverse in order traversal, which is nothing but moving to the right part, then root and then left. Okay, so what we would do is rec of root dash right. We would first visit the right and we would just pass the sum there. Then what we would do is we would store the value of root, because now we would be modifying the value of root, but we need the value of root in future. Okay, so I will just go back and tell you. Okay, so see, here we are modifying the value as 13, then plus 3 is equals to 16, but this 3 was required to have at this position. Okay, so that is why we would save the sum in a temporary variable and we would name it as temp. Okay, temp is equals to root dot data. We have just kept it somewhere and then we would modify the data of the root. Okay, so now root dot data is equals to sum we have received from the right hand side of it. Sum we have received. So see, right hand side is already visited. So right hand side is visited. This would give us the elements that are larger. Okay, elements that are larger. So we would replace the root dot data with the sum that is given. Then we would add the value of this temp. Okay, now this temp, we are increasing that sum because sum needs to keep going. Now we would visit what is remaining, that is rec of root of left and then the sum itself. Now we would need to call this. So int sum is equals to 0 and then we would have rec of root and then the sum itself, and then we would simply write return. Now let us just compile and run and see how many errors we are making. Okay, seems like we are not making any errors through the sample test case. Now let us submit this and see. Okay, so we have successfully solved it. Now let us do a dry run for a small tree where this is 4 and the left is 1 and the right part is 5. And this is a BST, why? Because the left is small and the right is big. So we can say that 4 would be replaced by the numbers greater than that. It is only 1, that is 5. 5, there is no 1, so 5 would be replaced with 0 and 1 would be replaced with 4 plus 5, that is 9. So now let us start doing the dry run. So first we would pass rec of the root, that is 4, with the sum as 0. So now the sum value is 0 at the moment. So now 4 is not equal to null. So what we would do is we would need to move on the right hand side of it. So we would move to rec of 5 with the sum is still the same, that is 0. Okay, so now rec of 5 needs to be done. So now 5 is not equal to null. So now rec of 5's right. So 5's right is equals to null, which would return from this position. So 5's right is returning. So I would just have this. Okay, so now we would have these all conditions, like we would initialize a temp variable where temp is equals to 5, that is root's data. Then what we would do is root's data is equals to sum. So 5 would be replaced with sum, that is 0. So 5 is now replaced with sum, that is, so we would keep writing it. 5 is replaced with 0. Okay, then what we would do is we would modify the sum with the value of temp. So sum plus temp is equals to 5. So now this would become 5, this would become 5, everywhere this would become 5. Why? Because this is passed by reference. Okay, now we would go to the left side of 5. So left side of 5 is null, so we would return from that position. Okay, so now the right part of 4 is done. If the right part of 4 is done, we would initialize a variable temp and we would store the value, okay, that is 4. And then what we would do is whatever is kept in the sum, we would assign it to the root. That is, now 4 would be replaced with whatever is assigned, that is 5. So 4 would be replaced with 5. Okay, then whatever is stored in the sum would get added to temp. Okay, so sum, whatever is stored in the temp would get added to the sum. So 4, 5 plus 4, that is 9. Okay, and then this right part is done, these all are done, then we would move to the left part. So we would move to the left part, that is rec of 1 with now the sum as 9. So what we would do is we would store this in a temp variable. Temp is equals to 1. Then we would assign 1 with the value that is stored in the sum. So 1 would be assigned with the value 9. And then we would add the value of the root temp to the sum. 9 plus 1, that would become 10. Okay, then we would move to the left side of 1. So left side of 1 is, so left side of null is equals to null point. So we would simply return from that position, and we can see that the values we have assigned just now is the same values that we have calculated manually. Now let's talk about the time complexity too. So we are visiting each node exactly once. So the time complexity is big O of n, and the space complexity is big O of 1, because we are only initializing the variables. We are not taking any auxiliary array or something. So that's it for today. Thank you and have a nice day.